we're going to break a rule. We're breaking one of the rules of Numberphile. We're talking about something that isn't a number. We're going to talk about infinity. So, infinity. Now, like I said, infinity is not a number, right? It's an idea, it's a concept, it's the idea of being endless, of going on forever. I think everyone's familiar with the idea of infinity, even kids. You start counting 1, 2, 3, 4, 5. You know, you might be 5 years old, but already you're thinking, what's the biggest number I can think of? And you go, ooh, it's 20. You get a bit old and you go, maybe it's 1,000,000. It never ends, does it? Because you can keep adding 1. So that's the idea of infinity. The numbers go on forever. But I'm going to tell you one of the more surprising facts about infinity. There are different kinds of infinity. Some infinities are bigger than others. Let's have a look. The first type of infinity is called countable, and I don't like the name countable. And Brady gave me a little bit of a just then, because if you're talking about infinity, you can't count infinity, can you? Because it goes on forever. I think it's a terrible name. I prefer to call it listable. Can we list these numbers? All right, let's do the simple numbers. 1, 2, 3.
You're not going to do all of my jokes.
4. How long have we got?
10 minutes.
All right, 5, 6. So you can list the whole numbers. So this is called countable. Listable, I prefer. What about the integers? All the integers. That's all the negative numbers as well. So there's 0. Let's have that. But there's 1 and minus 1. There's 2 and minus 2. There's 3 and minus 3. Now, that is an infinity as well. And in some sense, it's twice as big, because there seems to be twice as many numbers. But it is infinity as well. They're both infinity, and they're both the same type of infinity. They both can be listed. Perhaps more surprisingly, the fractions can be listed as well. But you have to be a bit clever about this. Let's try and list the fractions. I'm going to write out a rectangle. 1 divided by 1. That's a fraction, that's allowed. Let's have 1 divided by 2, 1/3, 1/4, 1/7. Okay, that goes on. Let's do the next row and have 2 at the top. 2 over 1, 2 over 2, 2 over 3, 2 over 4. Let's do the next one. 3 over 1, 3 over 2, 4 over 6, 4 over 7. That goes on, and we can keep going. So here I've made some sort of infinite rectangle array of fractions. Now, if I want to make a list like this, though, if I went row by row, you're going to have a problem. If you go row by row, I'll go this, there's 1, 1/2, 1/3, 1/4, 5th, 6th, 7th, and I'll keep going forever. And I'm never going to reach the second row. I can't list them, not that way. You can't list them that way. You'll never reach the second row. This is how you list them, slightly more clever than that. You take the diagonal lines. Now, I can guarantee that every fraction will appear on one of those diagonal lines, and you list them diagonal by diagonal. So that's the first diagonal. Then you list the second diagonal. There it is. Then you list the third diagonal. Then you take the fourth diagonal and the fifth. So eventually you are going to list every fraction. Every fraction appears on a diagonal, and you're going to list them. Now, if you take all the numbers, right, that's the whole number line. Let's try that. Look, I'm going to draw it. It's a continuous line of numbers. These are all your decimals. You've got 0 there in the middle, and you'll go 1 and 2 and 3, but it has a third. It will contain pi and e and all the irrational numbers as well. Can you list them? How do you list them? 0 to start with, and then 1, but hang on, we've missed a half. So we put in the half. Hang on, we've missed a quarter. We put in a quarter. We've missed 0.237. So how do you list the real numbers? It turns out you can't. And in fact, and rather remarkably, I can show you that we can't list them, even though we're talking about something so complicated as infinity.
Do it, man.
We'll need paper.
We need an infinite amount of paper here, I think.
It's a big topic. Imagine we could list all the decimals, right? We can't actually, but pretend we can. What would it look like? We'll start with all the 0 point decimals. Let's pick some decimals. 1, 2, 1, ... Let's pick the next one. Let's say the next one is 2, 2, 1. Next one, 3, 1, 1, 1, 1, 1, 2, 9, and let's take another one here. 0, 0, 1, 7, 6. Now I'm going to make a number. This is the number I'm going to make. I'm going to take the diagonals here. I'm going to take this number, and this number, and this number, and this number, and this number. Okay, and I am going to write that down. So what's that number I've made? It's 0.12101. Something, something, something. Now, this is my rule. I'm going to make a whole new number from that one. This is the number I'm going to make. If it has a 1, I'm going to change it to a 2. And if it has a 2 or anything else, I will change it to a 1. So let's try that. So I'm going to turn this into 0. So if it has a 1, I'm going to turn it into a 2. If it's anything else, I'm going to turn it into a 1. So that will be a 1. I'm going to change the 1 here into a 2. I'm going to change that one into a 1. I'm going to change that one into a 2. That was my rule. And I make something new. That does not appear on the list. That number is completely different from everything else on the list because it's not the first number, because it's different in the first place. It's not the second number, because it's different in the second place. It's not the third number, because it's different in the third place. It's not the fourth number, because it's different in the fourth place. It's not the fifth number, because it's different in the fifth place. You've made a number that's not on that list. And so you can't list all the decimals, in which case it is uncountable, it is unlistable, and that means it's a whole new type of infinity, a bigger type of infinity.
Surely we could, James, because all we've got to do is keep doing your game and making them and adding them to the list. And if we keep doing that, won't we get there eventually?
But you could then create another number that won't be on that list. So the guy who came up with this was a German mathematician called Kantor. Kantor lived round about the turn of the 20th century. He was ridiculed for this. For this idea that there are different types of infinity, he was called a charlatan. And he was called, it was nonsense, it was called. And poor old Kantor was treated really badly by his contemporaries, and he spent a lot of his later life in and out of mental institutions where he died in the end. Near the end of his life, it was recognized. It was true, it was recognized, and he had all the recognition that he deserved.
And now he's on Numberphile.
And now he's on Numberphile, the greatest accolade of all. George Kantor.